Hi everyone, and welcome to this video on Introduction to Rational Expressions Part 2 of 2. In this video, you will learn how to find excluded or restricted values of rational expressions. Please note that the terms restricted values and excluded values are used interchangeably by this instructor. The textbook currently uses the phrase excluded values. Food for thought. Why are excluded values important? Excluded values or restricted values force us to restrict the domain of a function, a concept that will be explored further in a later chapter. We also find that interesting things happen to the graphs of functions when we try to divide by zero. So let's go and start an example. So example 1 says to find all excluded or restricted values of the rational expression. Again, I'm using the terms excluded and restricted interchangeably. So the steps that we have, first we're supposed to set the denominator equal to 0. Well, what is the denominator in this fraction? Well, the denominator is 3. If I write 3 equals 0, what happens? Is 3 ever going to be equal to 0? No, this can never be true because 3 is a constant, not a variable. Therefore, we don't have any need or any reason to restrict the values of the variable in this function. In fact, if you look at it, 2 over 3, it's not a function at all. It's just a number, okay? So we do not have any restrictions. We have no excluded values or no restrictions. So when I'm teaching this in a class, it's kind of silly, but I like to think about it as like babysitting, right? So if you babysit, I don't know, like a 1-year-old or a 2-year-old, it's going to be an entirely different experience from babysitting a 12-year-old, right? If you babysit a 2-year-old or a 1-year-old, somebody who's really small, you have to watch them a lot more. They, might put things in their mouth that they shouldn't. They might try to touch something hot, right? Whereas a 12-year-old is probably gonna, be alive by the end of the night, no matter what you do. You know what I mean? They're probably a lot safer. So the restrictions that you have to apply to a 2-year-old versus a 12-year-old are very different. So that's kind of what we're thinking about here. Right? What are the restrictions? So remember the thing here, mathematically, right? The reason we have to have a mathematical restriction is because we cannot divide by 0. We can't ever let this happen, okay? I made a whole video of why we can't divide by 0. So if you're really curious and wondering, well, what happens graphically or what happens numerically when we try to divide by 0, feel free to watch that video. Okay, so then example 2, we have 2x over 3. So again, we're still just looking at the denominator because, the numerator can be 0. We can have 0 divided by 3, that's fine. The only problem is that we can't divide by 3. So again, if I look at 3, well, when is 3 equal to 0? Well, 3 is just a number. 3 is always 3. 3 is never going to be 0. So again, I have no excluded values or no restrictions. So as long as my denominator is a constant, as long as there are no variables in the denominator, I have no excluded or restricted values. Okay, so this is getting a little bit boring, so let's go to example 3. Finally, at long last, we actually have a variable in the denominator. Okay, so we're going to set 3x equal to 0, and then we're going to solve for x. So we divide both sides by 3, and we get x is equal to 0. And what we're really saying is, we're saying that x can never be equal to 0. Right? Because if x equals 0, what do we get? Well, we get 2 over 3 times 0, or 2 over 0. Okay, and again, just like babysitting, right? If you have a little kid, you don't want him to put something poisonous in his mouth, right? That can't happen. You're not allowing that to happen. Same thing in mathematics. We can't let this happen. Okay, so we write the equal sign with a slash through it, and we read that as not equal to. So x cannot be equal to 0. So this is my excluded value or restricted value. And that's it. So let's do another example. Okay, example 4, I have 2x over 3x. Now, if you pause this video for a minute and just kind of look at this, you might think to yourself, well, gee golly, the x's could cancel out, and then I would just have 2 over 3. And if I did that, then I wouldn't need any restricted values at all. Well, believe it or not, you still have restricted values. You still have to make sure that x is never equal to 0. And I'll tell you why. Okay, because if I had 2 times 0 over 3 times 0, well, that's 0 over 0. Guess what, everybody? 0 over 0 is still undefined. It's not 0. Okay? So even if the numerator has an x in it as well, right? Even if the x's would cancel out, I still actually have a restricted value. Okay, and as you advance in this class and another class and you start graphing these functions, you'll see what happens graphically to the function f of x when x either equals 0 or gets really close to 0. Okay, all right, so we do the same thing as in the last problem. We have 3x cannot be equal to 0. No, can't let that happen. 0 divided by 3, of course, is 0. So this is it. This is my excluded value, or you might hear restricted value. Sometimes I use that term. Okay, so we set our denominator equal to 0. We solve for our variable, and we listed our values, and that was it. All right, let's do a few more examples. Example 5, okay? So again, we just look at our denominator, don't really care what our numerator is doing. Okay, we tell ourselves x plus 2 may never be equal to 0. So then we proceed to solve for x, just like we would in a regular old algebra class. So we say that x can never be equal to negative 2, right? And that kind of makes sense, right? Because if I put negative 2 back in here, well, negative 2 plus 2 is 0, right? And we've already said, kind of beating a dead horse here, we cannot do that. We cannot divide by 0. If you did, it would be undefined. Graphically, you get either a vertical asymptote or you get a hole in your graph depending on what your function looks like. Okay, so again, this would be our excluded or our restricted value. Okay, all right, one more example here. So we have x squared plus 9x plus 20 divided by x squared minus 16. Okay, so again, I cannot emphasize this enough. We really don't care about the numerator right now. We will care about it later when we do other things, like reducing rational expressions, but we're not there yet. All we're trying to do right now is find our restricted values. And, the restricted values, again, only come from the denominator. They come from the denominator, right, because we cannot divide by 0. Okay? So, hopefully this is triggering your memory and your spidey senses are tingling and you're thinking to yourself, OMG, that is a difference of squares and I can factor it. And that is in fact exactly what we're going to do. Okay, it is a difference of 2 squares, so we factor it and then we set both linear terms not equal to 0, right? Because again, these are restrictions. These are things that can never happen, not things that could or should happen. Okay, so we have either x cannot be equal to negative 4, or of course x cannot be equal to positive 4. So we can just sort of list them here, separated by a comma. So we could say x cannot be equal to negative or positive 4. So again, in this example, you would have not 1 but 2 excluded values.